Okay, so I'm going to give you guys iterated integrals over rectangles. And I'm just going to actually do this by example because I claim you know how to do this already. So we're going to integrate from 0 to 3, and we're going to integrate from 1 to 2. And our function for this example is going to be x squared y. And we're going to do dy dx. Okay. This doesn't look like the thing we were just doing, right? Nope. Because a minute ago we were just doing things that had a d area at the back, right? You guys with me? And had like an integral over r. And at least in this case, that x squared y thing, right? That makes sense. That's a function of x and y, right? So at the very least, that part is the same. Now, what the heck is this double integral nonsense?
You do the inside integral and the outside integral, and you do it with respect to the dy and then dx.
Yeah. Okay, so let's just try this first, and then I'll explain why this is actually the same thing we've been doing. So Karina says, don't be dumb. Just what now?
Do your inside integral with respect to your dy.
Okay, so I'm going to leave the 0 to 3 on the outside and the dx on the outside, right? But this is order of operations, right? You go to the deepest grouping symbol and do that shit first. Yeah? Okay, it's not magic, right? Just do the thing you've always done. Okay, so how do you integrate dy x squared y?
X squared is constant and integrate for y.
Yeah, x squared's a constant. You're integrating with respect to y, right?
On the interval of 1 to 2.
So you got an x squared, and you should have a y.
Should be a 1.
You guys remember how to differentiate? Or
Should be
how
1
to?
half y squared,
Yeah.
correct?
Okay, y squared over 2. And then, where'd your plus c go?
It's on the interval of 1 to 2.
Yeah, good.
Yeah.
Don't put the plus c in there because you're doing a definite integral, right? This should be evaluated from 1 to 2. And at this point in your lives, it might be a good idea to write y equals 1 to y equals 2. You guys do that usually or not?
It's good for you to do now,
Why do I want to do that now?
so that we don't confuse it with x.
Good. Right? Because you want to plug in 1 and 2, but they need to go in for the y's, not for the x's. You guys with me? So be careful with these. I don't care whether you put them there or not, just get the problem right. So we should have the integral from 0 to 3 of what?
2x.
2x squared minus 1 half x squared.
Yeah.
2x squared minus x squared over 2. Perfect. And we're integrating dx, right? You guys with me? All right, so we plugged in y as 2, we got 2x squared, then we plugged in y as 1, and we subtracted. Awesome. Now,
No.
That-
3 halves x squared.
Yeah, let's just make that 3 over 2x squared so that we don't have to deal with the, so we don't have to deal with x's in multiple places.
cool. Yeah, combine like terms to make your life easier, right? So you can, if you combine like terms now, you can integrate once. Otherwise, you'd have to integrate 2 different functions and get it right. They're the same function, so hopefully it's not hard, but whatever. So let's say we combine like terms, right? And we got the integral from 0 to 3 of 3x squared over 2 dx. Okay? For reference, right? This was a integrate with respect to y step, and then we evaluated, and then we combine like terms, and now we should what?
Integrate. Yeah, integrate again. This time
Integrate with
x.
respect to x. Okay, so when I integrate with respect to x, I'm going to get what?
It's x cubed over 2, then with respect to x equals 3 and x equals 0.
X cubed over 2, right? 1 higher power over the 1 higher power, the 3's cancel. and we're evaluating from x is
0.
0 to x is 3. Where'd the dx go?
It's part of that kind of, it's how we integrate it.
Yeah, you used it,
Yeah,
right? Okay, so now,
we get 27 over 2 when we just do math.
okay. What's 27 over 2 mean?
That's the area of this?
That's the volume.
That's the volume under the surface. G of x and y is x squared y. You guys see that? So I said that's the volume under g of x and y is x squared y. But
In that, like, domain.
yeah, over the rectangle what? What's your rectangle?
The XY plane?
No,
It's part of the xy plane. The rectangle lives in the xy plane, but the rectangle itself is where?
0 to 3 and 1 they go.
Oh,
Yeah, those are the slices that made up this integral, right? So in the x's, where does this thing range?
Either or.
Good. So it's over the 0 to 3 by 1 to 2. Okay, now I think I probably just cheated a symbol. Have you guys seen this symbol? Did I give you this symbol yet for multiplying intervals?
Product.
Yeah, this is not a cross product because these are not vectors. You guys all see that? This is the by symbol, like 2x4s. You guys cool with that? So this is the interval in the x by the interval in the y.
And x is always first thing if you're using that notation.
Yeah, and x always comes first if you're using this notation. If you want a rectangle with more dimensions, if you keep adding by's, they go in x, y, then z, and then they turn into x1, x2, x3, x4, right? You guys remember that convention? We go to z's and then we do something else. So about this thing, you should be thinking, let's see, so x and y, right? So 0 out to 3, and in the y's we're starting at 1 and going to 2. So the rectangle I'm looking at is this one. Oops. That one. You guys with me on that? Okay. And we're actually counting up everything inside of here, right? Does it matter whether the edge is included or not?
If they weren't included, that'd be less values, right?
No, you can't.
Would it?
Bounded.
How much volume's over the edge? How thick is the edge? Yeah, it
I'd
doesn't.
say in real world applications, it wouldn't matter.
Yeah, it turns out in math it doesn't matter either. Because right, what you should be doing is taking these little areas, right, and multiplying by their height. That gives you a volume. Well, if you pull the edges out of this thing, right, they don't have any area. So even if you take that 0 and multiply by the height, who cares? It's still 0 volume that you're adding or subtracting.
it just makes it
You guys see that?
exact so that we can actually use it as like a max and min and stuff like that, correct?
It turns out it doesn't matter at all.
Oh, okay.
So if you're integrating over something with the edges or without the edges, you can just assume the edges are in there because it'll make your brain work better.
Yeah.
Cool?
Okay.
And that'll hold exactly until we start hitting shit with hammer and differential equations. And there we'll have to pay a little closer attention.
technically though, like if you had a function that's undefined on an edge,
Yeah.
then it would matter in that case, you know, in math.
Yeah, as long as the height is finite, right? Then I can say this thing about, well, the height times the area should be the volume you're discounting. If the height's finite and the area is 0, then you get 0, so who cares, right? But if the height's infinite at that edge, then there's a problem, right? Because I don't know what infinity times 0 is. You guys see that?
We can assume.
Infinite or just
but-
undefined, if there's a hole there. You have a function for a hole, you know,
If-
x equals 3.
If the limit goes to a finite value, you'll be fine anyway. It's super cool, you can get away with it. But if the limit goes to an infinite value, yeah, there's a problem. Cool? All right, so let's try this the other way, just for kicks. Remember, we got 27 maps.
Oh, so now we're gonna do the x, y, dA.
So I'm actually just going to reverse this thing.
Ah,
So I was doing 1 to 2 in the y's first, and then 0 to 3 in the x's. And so let me switch the spots. So I'm going to do the x's first, and the x's went from 0 to 3. And the y's, where did they go? 1 to 2. Okay, so let's try this again. Hopefully we get to 27 over 2. Right? Okay, so what do you get when you integrate dx first here?
1/3 x cubed y.
Okay, so you get the integral from 1 to 2 of x cubed y over 3 evaluated from 0 to 3 dy. You guys with me? Okay, so then you get the integral from 1 to 2 of
9y.
9y.
Once we do the integration. Oh,
Did I lose you guys?
Yeah, would you plug 3 into the y and the 3's cancel out, and you have an x cubed?
That's an x.
Oh.
Right? Because I integrated dx, so my evaluation should be with respect to x. And then I'm integrating dy. One thing you can do for this is you can think to yourself, okay, I integrated dx. At the end of that step, there should be no more x's. You guys see that? That's going to be true regardless of whether you're integrating over rectangles or not. It's actually a really good check to see if you constructed these things right. In a minute here, we're going to get to the point where we construct these things, the bounds. And over more general regions, you might have some formulas in there. But this always holds. Once you've integrated the x's, they should be gone. If there are still x's in this thing, you got problems because you won't get a number out at the end. You guys see that? Okay, so what do you get out of this?
9 over 2 y squared.
Okay,
Evaluated at
so you got
interval of 1 to 2.
9y squared over 2, evaluated from 1 to 2.
27 over 2.
Hey, cool. You see that?
Yep.
That's really neat. So why does this work?
Commutative property?
Yeah, the commutative property of addition, right? This is, right, I took this rectangle that I was working with that was 0 to 3 in the x's and 1 to 2 in the y's, right? And the first time I I integrated the y's out, right? So that was setting a specific x and adding up across, oops, I just said setting a specific x and then adding up across the y's. So that's like this, right? So that's adding columns first and then adding up all the columns. So that was our first attempt, right? And our second attempt, what was the only difference?
You just start with
Yeah, we added up the x's first, right? So we integrated with respect to x first, and then we added all those up. Does it matter? Better not, right? Like that was that thing about does it matter if I add by columns or by rows? No, shouldn't. Are there other ways to add? Oh yeah, you could do like some weird other pattern, right? There's a way to get another pattern. You could do polar, right? You could make yourself another pattern. This execution that I've been doing is a realization of doing this integration over the area thing, right? So what exactly I'm doing is I'm saying, okay, there's a rectangle, right? That rectangle goes from 0 to 3 in the x's and 1 to 2 in the y's. And then how do I add up area over that thing? I chunked it. I took little x bits and little y bits, and then I added either the columns or the rows first. Doesn't actually matter, right? But somehow I get a realization for area out of this thing. You guys see that? This whole idea, right, is just you're going to sum up a bunch of little heights times some kind of change in areas, right? However you do that is up to you. I would suggest these. They're good methods. They're easy when you have things that are written as functions of x and y. Are they always the best methods? No, not really. If you're dealing with circles, you might want to invent this for polar. If you invent this for polar, you should be careful. D area is not dr d theta, like you might want to think it is. You need some kind of a, hey, this isn't a rectangle factor in there. You guys cool with that? We'll get to that later. Like, we'll invent that in a little bit. But for right now, I just want you guys to know it's not rectangular, don't treat it like this. Cool? Good? All right.